Greetings, everyone. In this video, we will go through some of the basics about machine learning and artificial intelligence. Let's begin with the question, what is machine learning? Machine learning is a branch of artificial intelligence that focuses on the use of data and algorithm to imitate the way you and I, humans, learn and gradually improving its accuracy over time. An icebreaker activity that I like to do, um, especially if it's asynchronous or in class, but it doesn't matter whether you're listening to this or it's an online class. How about we engage in this one? Think about when you hear these two words, machine learning and artificial intelligence, what is the first thing that comes to your mind when you hear those? Pause for a second and think about that. This is an optional slide, but it doesn't hurt to engage in this activity. I still have the question and the QR code if you'd like to do that. And then if you scan it or you want to go online and answer with one word. Here are a few possible answers from your peers, and of course, they will be changing as there are more people that are participating in this activity. And you can see from automation to algorithm to automation, of course, is taking over repetitive tasks such as robotic process automation in factories, for example. There will be answers such as clustering, classification, and so many more, whatever you think about those. So this will be changing as more of you engage into this activity. Let's engage a little bit more into that activity, but through some of the answers. We look at it from a robotics perspective, or robots. What technologies are essential for robots to function effectively? How do these technologies shape the way robots interact with the environment? And one way to look at it is robots, they rely on several key technologies. At the core of modern robotics is AI, artificial intelligence, which enable robots to process information, learn from the data, and make decisions. For example, AI allows robot to recognize patterns, such as distinguishing between different objects or navigating a room. Think of Roomba, right? Machine learning, which is a subset of AI, plays a critical role by allowing robots to improve their performance over time. So through machine learning, robots can learn from past experiences, adjust their actions based on the outcome, which is pretty much like humans, how we learn from our mistakes and successes. Another important technology here will be computer vision. And I'm sure you heard about computer vision, which helps robots see. See, I would put that between quotes or brackets because we humans see and the robots, that gives them a way to interpret their surrounding. How do they do that? By using cameras, sensors. Robots can map their environment and understand spatial relationships. And this enables them to move safely around obstacles and interact with objects. One of you has watched some AI-based movies, right? Whenever we think again about machine learning and AI, we think about these movies. How do you think the portrayal of AI in movies differ from the reality of AI today? Here's one way to look at it. In movies, AI is often portrayed as highly advanced and capable, like human intelligence, and even surpassing um, human abilities. For example, we see some of the movies like Robot or Transcendence. The AI systems are uh, depicted with the ability to think, to learn, and even have consciousness similar to humans. Today, AI excels at several tasks such as image recognition, such as language processing, but it still lacks the general intelligence, self-awareness, and emotions that often we see in movies. You may, by the time you listen to this presentation, things could be changing. Are they self-aware? Will there be emotions involved? Most AI systems are based on machine learning algorithm and they require large amount of data and they can function within the confines of the data they've been trained on. Um, they are not so I'm hesitant here. They're not as autonomous in the way that movies suggest. That said, things can change as we speak. Another aspect about AI-based movies is these movies depict AI as potential threat to humanity, whereas in reality, AI development is more focused on augmenting human abilities and solving complex problems, such as in healthcare, finance, and environmental management. So, while there are concerns about AI ethics and safety, the AI takeover scenarios from films are um, are probably not the reality we'll live right now, but I'm going to leave you with that. Or is it? Use one of these AI tools, right? And ask them directly, what is machine learning? You can call Google, Alexa, Siri, or whatever. And what is machine learning? And one of them will give you a definition similar to the one you see on your screen, which is a scientific study of algorithms and statistical math models that computer systems use to effectively perform a specific task without using explicit instructions, the keyword explicit instructions, relying on models and inference instead. Here's another longer definition of machine learning from Wikipedia. Take your time to read it at your leisure. In simple terms, machine learning is all about using data from the past to predict outcomes in the future. First, we gather historical data and use it to identify patterns or trends. We then build models based on this data, which are essentially mathematical representations of the relationships within the data. Once we have our models, we can train them on a set of data. This is called training data. The models learn from this data, recognizing the patterns and making associations. After it's trained, we can use the model to make predictions on new and seeing data, such as forecasting future sales or detecting potential fraud. So, at the core, machine learning is about teaching a machine to recognize patterns in data so we can make predictions without being explicitly programmed for every scenario. Data comes in various forms, each serving different purposes in machine learning and AI systems. These forms of data help machines learn and make predictions in diverse applications. In the next few slides, we'll look at different types of data from numerical, image data, video, sound, and text data. Take a look at numerical data and explore a few examples of how numerical data is used in different fields. For example, look at credit risk models. We all know banks analyze historical data such as credit scores, payment history, and income levels to predict whether a customer is likely to default on a loan. This predictive model helps lenders make informed decisions and mitigate risks. Marketing analytics, let's talk about marketing calls, and I'm sure you all have received marketing calls or text messages or targeted for specific products or campaigns. Companies right now, they use data such as past purchases, browsing behaviors, and demographic information to create profiles and tailor their marketing campaigns to individual preferences, improving their chances of reaching the right audience. The example of retail sales analytics also relies on numerical data to offer personalized promotions. For example, you might receive offers for clothing or accessories, which someone else may get while someone else may get promotions for apartments or cars or something else. This differentiation occurs when retailers analyze your past purchases history and preferences to predict what products you're most likely to buy, making their marketing again more effective. Last, we have an example of fraud analytics, which helps financial detect potential fraudulent transactions from millions of credit card swipes. Using advanced algorithm, banks analyze transaction patterns, spending behaviors, and location to flag suspicious activities. This allows them to quickly identify and prevent fraud, protecting both the consumer and the financial institution. Machine learning applications involve images and videos. They're becoming increasingly common and impactful in today's world. Let's take a closer look at some of these applications. First, face recognition. What it does, it uses image data as an input to verify or identify a person's identity based on facial features. And this technology is widely used in security systems, airports, social media, and even smartphone authentication. Machine learning models analyze various facial landmarks and patterns to recognize individuals with high accuracy. The next example will be object recognition, which involves identifying and classifying objects within images by analyzing the pixels that make up those images. For example, this technology can help autonomous systems recognize pedestrians, vehicles, or even specific items in retail or industrial settings. Now let's talk about digit recognition is another essential application where machine learning models interpret handwritten text or characters. This has been particularly useful for digitizing handwritten forms, automating check processing, or even improving optical character recognition systems that convert images of text into machine-readable data. Last, self-driving cars. They're an advanced application of machine learning that relies heavily on video data, and these systems use video feeds from cameras mounted on the vehicle to detect and track objects like cars, pedestrian, road signs, and traffic signals. And by processing real-time video data, self-driving cars can make decisions such as when to stop, turn, change lanes, which ultimately aim for safer and more efficient transportation. Do you see number 6? When we look at an image, we perceive it as a whole object or pattern. For example, here we see the digit 6 in a simple pixelated format. This is how human vision works. We can quickly identify the digit based on our experience and cognitive abilities. However, for a computer, understanding an image involves converting it into numerical data. What you're seeing on the right side of the slide represents how computer vision works. The image is broken into pixels, and each pixel is represented by a numerical value corresponding to its intensity or how light or dark the pixel is. These numbers help the machine identify patterns in the data. In this case, the machine learning model interprets these pixel values to recognize that the shape forms the digit 6. This process of converting image data into numbers is at the core of how machines are trained to understand visual information. They don't see the image in the way us humans do. Instead, they analyze numerical patterns in the pixel grid. By processing these numbers, the computer can make decisions about what it is seeing, and through training, it becomes better at recognizing specific objects or characters, like digits in this case. Data is incredibly powerful, and machine learning is enabling new applications that extract valuable insights from it. Some of the key applications of machine learning on text data include sentiment analysis, topic extraction, and document classification. So let me talk a little bit about each. Sentiment analysis is one of the most popular applications of text analytics. This process involves analyzing text data to determine the sentiment behind it, whether it is positive, negative, or neutral. Extraction of key topic involves identifying and summarizing the main ideas within a large set of text. This technique is widely used in media analysis, customer feedback reviews, or any scenario where it is important to identify recurring themes or concerns within large volumes of text. And the last, document classification. This involves organizing text into predefined categories based on their content. This is especially useful in industries like healthcare or law, where large numbers of documents need to be processed and classified quickly and efficiently. What is AI? AI refers to the creation of intelligent machines capable of performing tasks that typically require human intelligence. These tasks can range from visual perception, speech recognition, decision-making, and even language translation. AI systems are designed to simulate human thinking, but they process information at speeds with high levels of precision that far exceed our capabilities. There are 3 types of AI. At the base of the pyramid, we have step 1, machine learning, also known as narrow artificial intelligence, or ANI. This step includes system design to perform specific tasks with a narrow focus. These systems do not possess general intelligence. They excel only within their defined domain. For example, ANI examples include digital assistants like Siri, Alexa, Google, and others. They're very effective at tasks like setting reminders, playing music, or providing weather forecasts. But they cannot understand or perform tasks beyond their programming. Moving up the pyramid, we reach step 2. Machine intelligence, also known as Artificial General Intelligence, or AGI. This represents AI systems capable of understanding, learning, and applying knowledge across a wide range of tasks, similar to human intelligence. AGI would allow machines to perform any intellectual tasks as a human can do, including reasoning, problem solving, and adapting to new situations. At the top of the pyramid is step 3, machine consciousness, I can't pronounce that word, also known as ASI or artificial superintelligence. This step envisions AI systems that surpass human intelligence in every aspect, including creativity, problem solving, and even emotional intelligence. ASI would have abilities far beyond human capabilities, potentially including consciousness and self-awareness. This step represents a state of AI development that scientists and ethicists continue to debate and explore. At the next level, we have artificial intelligence, which we talked about in the previous slide. Within AI, there is machine learning, which focuses on algorithms that improve the performance as they're exposed to more data over time. Instead of being explicitly programmed for every task, these algorithms learn from the data they process and make better predictions as they receive more examples to learn from. And this is the core of this class. Deep learning is a type of machine learning that takes this one step further. It is inspired by the structure of the human brain and uses neural networks, computational models made up of layers of artificial neurons that process a vast amount of data. By using multiple layers, deep learning model can identify intricate patterns in data, making them particularly effective in tasks like image recognition, natural language processing, and autonomous driving. So while deep driving is one aspect of the broader machine learning field, its ability to process and learn from enormous data set with complex structure is what makes it such a powerful tool in modern AI applications. Learning algorithms attempt to replicate how humans draw conclusions by continuously analyzing data in a structured way. To achieve this, deep learning uses a multi-layered structure of algorithms called neural networks. A typical neural network consists of multiple layers of interconnected nodes. These nodes or neurons process and transform the input data as it moves through each layer. The layers in between the input and the output are called hidden layers. Each connection between the nodes carry a weight, represented here as W1, W2, W3, and W4, which adjusts as the network learns from the data. Just as our brain identifies patterns, learn from experience, and classify information, we can train neural networks to perform similar tasks on data. These networks can recognize images, translate languages, drive cars, and much more by learning from all these large amounts of data and improve their accuracy over time. Now that you have a holistic idea of key terminologies used in AI, let's focus on machine learning, the core of this class. The process of building a machine learning model begins with training data. This is the foundation on which the model learns. The training data consists of a large set of examples, like the binary data you see here, which could represent anything from images to text or even sensor data. The goal is to feed this data into the machine learning algorithm so it can learn patterns and relationships within the data. Next, we build the model.
This involves training the machine learning algorithm to recognize patterns and make predictions based on the training data. This step involves setting up a structure, like neural networks or other type of models, where data flows through various layers of interconnected nodes or neurons. Each connection between nodes has a weight associated with it, and these weights are adjusted during training to minimize errors and improve the model accuracy. In this model building phase, mathematical functions are applied to the data as it moves through the network. These functions calculate the weighted sums of the input, apply activation functions, and adjust the weights in each layer. This allows the model to learn complex relationships within the data and improve its performance. As the training process continues, the model becomes better and making predictions on new and seen data by generalizing from patterns it learned during training. The more data we use to train the model and the more iterations of training we go through, the more accurate and reliable the model becomes in solving real-world problems. Ultimately, machine learning models are built by training data, adjusting weights and parameters through algorithms, and continually improving their ability to make accurate predictions. We have trained our machine learning model using historical data. We can now apply the model to new data. As you see here, the new data is fed into the model that we previously built. The model uses patterns it learned during training to make predictions based on this new input. This process involves passing the new data through the same layers of neurons and weights that were used during the training phase. This model applies the learned relationships and mathematical functions to new data, eventually generating an output which is the model's prediction. In this example that you have right here in this slide, the model predicts that the data belongs to class 2. This prediction could be correct or incorrect, depending on how well the model has generalized from its training. As you can see in the diagram, this type of model is a one-way model, meaning the prediction is made in a single pass through the network. After getting the prediction, we can validate its accuracy by comparing it to the actual results. This helps us refine the model further or make necessary adjustments to improve its performance. What we ultimately seek in AI systems is reliability and accuracy in their predictions. In many AI systems, the key to continuous improvement is incorporating a feedback loop into the machine learning model. So let's talk about it a little bit more here. Initially, we trained the model with a data set, as shown on the left. The model learns patterns from this training data and uses them to make predictions, such as classifying new data into class 2, as shown on the right. However, the process doesn't end here. Once a prediction is made, we assess its accuracy. If the prediction is correct or could be improved, we provide feedback to the model. The feedback is used to update the training data and potentially add new data points that reflect the correct outcome. This updated data is then fed back into the model to update the model's parameters, its weights, and biases so that it becomes better at making accurate predictions in the future. This iterative process, known as feedback loop, allows the AI model to learn from its mistakes and refine its performance over time. That we have explored how machine learning models learn from data through feedback loops, it is important to remember that these models rely heavily on statistics to function effectively. In machine learning, we often work with large data sets, but just like in traditional statistical analysis, we we can't always observe or analyze an entire population. The power of statistics lies in its ability to allow us to make informed decisions or predictions about a broader group using only a fraction of the data. This process is crucial in all fields, whether it's healthcare, marketing, social sciences, where we often rely on samples to guide important decisions. In statistical analysis, the main goal is inference. This means using a small, observed sample of data to make generalizations or draw conclusions about a larger population. For example, or the illustration you have in front of you, we have a population, which is the entire group of individuals or data points that we are interested in studying. However, it is often impractical or impossible to analyze the entire population due to size, cost, time constraints, or others. Instead, we take a sample, a smaller, manageable subset of the population. The sample is carefully selected to be representative of the population so that we can make more accurate inferences. By analyzing the data in the sample, we apply statistical methods to make educated guesses about the characteristics, behaviors, or trends within the entire population. For example, in a research survey, we might collect data from a small group of people, and based on the analysis, we can infer conclusions about the entire population's preferences or opinions. Building on our understanding of how machine learning models use feedback loops to improve, the next step is ensuring that these models can generalize, meaning that they can accurately predict outcomes, not just on the data they've seen, but on new and seen data as well. So the main objective of predictive modeling is generalization. This means this refers to the model's ability to accurately predict outcomes on new data. This process starts with training data, which represent historical information or observations. This data is used by an algorithm which learns patterns and relationships within the data. The algorithm then generates a model, essentially a mathematical representation of the learned relationships. Once the model is built, it should be able to generalize the patterns it has learned to new data that was not part of the training set. This is critical because the ultimate goal is for the model to make accurate predictions in real-world scenarios, not just the specific data it was trained on. Let's look at a real-world application of predictive modeling, credit card and loan approvals. I'm sure you have applied. I'm making an assumption you have applied for a credit card or store card and received an immediate approval or denial. And probably in some cases it was on a weekend or holiday when the banks are usually closed. How does that happen so quickly? This is where predictive modeling comes into play. When you submit your application, whether for a credit card or a loan, the bank uses a predictive model to make an instant decision. The model has been trained on a large data set of past applications, analyzing factors like your credit score, your income, your financial history, to predict whether you're likely to repay the loan. In just few seconds, the model classifies your application, either approving it or declining it, based on patterns it has learned from previous applicants. The bank does not need a human being or human intervention because the model generalizes based on past data, which allows it to predict the outcome of new and seen applications. This system helps bank managers to manage risk effectively while offering quick and reliable decisions to customers, of course, thanks to predictive modeling. When banks assess your application for a credit card or a loan, they use predictive models to make decisions based on a variety of factors. These models evaluate your financial information and history to determine the likelihood that you'll be able to repay the loan or manage credit responsibly. For instance, if your income is high, the model might approve your application. Similarly, if you own a home or a house, this might increase your chances of approval as it signals financial stability. However, the decision-making process must be rooted in relevant data. As you can see in the third point on the slide, a model shouldn't reject someone's application because their best friend is Peter. That would be irrelevant and a sign of faulty model. The purpose of a well-trained predictive model is to use accurate and meaningful data like income, credit score, or employment status to make fair and reliable decisions. Look at this scenario. What happens if Peter is a gambler? Could that influence the bank's decision? In this case, if Peter's gambling habits are linked to your financial behavior, such as if you co-signed a loan with him or shared financial accounts, then it could indeed impact the model's decision. Predictive models take into account financial risk factors, and if you're financially connected with someone higher risk behavior, like gambling, it might signal a greater likelihood of default. However, if Peter's gambling has no direct financial connection to you, meaning you don't share any accounts, loan, or financial responsibilities, then his habits should not impact your application. A well-trained and fair predictive model should focus on your financial data, not the behavior of others, unless there is a clear link. Of course, there are some scenarios where knowing Peter or being associated with a person with high risk profile could potentially lead to denial, depending on certain circumstances, such as co-signing loans or joint financial account, shared address or residency, credit history association, fraud detection system. If, for example, Peter is flagged for fraud or money laundering, in such cases, the model would not be considering the mere fact that Peter is your friend, but rather the financial risks associated with him. Every day, more than 100,000 customers apply for credit cards and loans. Each applicant has unique characteristics, different incomes, credit histories, and financial behaviors. But here's the challenge. Out of all these customers, who poses the highest risk of defaulting or not paying back their debt? Essentially, the bank needs to determine who will run away with their money. This is where predictive modeling becomes crucial. By analyzing patterns in customer data, banks can predict the probability of default or the likelihood that someone will take a loan or credit and fail to repay it. The bank's goal is to identify those higher risk individuals before approving loans or credit. Predictive models help solve this problem by assessing each applicant's risk profile and helping the bank make informed decisions. How to predict? When it comes to predicting outcomes, whether it's identifying who might default on a loan or forecasting future sales, we have two key tools at our disposal: historical data and statistics. Historical data provides us with wealth of past information. By analyzing trends, patterns, and behaviors from the past, we can make informed predictions about what might happen in the future. In essence, the data tell us a story. But as this humorous quote by economist Ronald Coase reminds us, if you torture the data long enough, it will confess. This highlights the fact that while data is powerful, it can sometimes be misinterpreted or manipulated to tell a certain narrative. This is why statistics and rigorous analytical methods are so important. They help us avoid torturing the data and instead uncover true, reliable insights. Let's use a horse racing analogy to better understand predictive modeling in finance. Imagine you're at a racetrack trying to decide which horse to bet on. Each horse represents a different applicant, and your goal is to predict which one is most likely to win, or in the case of banking, which applicant is most likely to repay a loan. You wouldn't just pick a horse at random, instead you look at historical data. How has the horse performed in the past? Was the horse trained in regiment? Was the track record of jockey? Similarly, in predictive modeling, banks rely on historical data about applicants, such as their credit score, income, and previous behavior to predict their likelihood of success. Just as you use past performance to bet on the best horse, banks use data to bet, I use that between single quotes or double quotes, on the best applicants. The better the data and the model, the more accurate the predictions will be. Now, let's take a look or a closer look at the historical data to predict the winner of a race. Just like in banking, where we analyze customer data to assess risk, in horse racing, we examine key characteristics that have been strong predictors of success. In our case, historical data for a horse could be as follows. Long legs. Horses with long legs have won 75% of the time. This tells us that leg length is a strong predictor of success. Breed. Breed A, horses have 55% success rate, while breed B horses have only 15% success rate. The rest fall into the others category with a 30% chance of winning. Tummy to length ratio, T over L. Horses with a tummy to length ratio of less than 1 to 2 wins 75% of the time. This unusual metric may correlate with high agility or stamina. Next is gender. Surprisingly, male horses have a lower success rate, winning only 32% of the time. Head size. Horses with a larger heads have a 75% win rate compared to those with medium or small heads. Country of origin. Interestingly, horses from Africa have a lower win rate of 35%. So by analyzing these factors, we can identify patterns and make more informed predictions about which horse is likely to win the next race. Similarly, in predictive modeling, we'll look at historical data and key indicators to predict future outcomes, whether it's for betting on a horse or assessing a loan application. Now that we have examined the key historical factors that influence horse racing outcomes, it's time to put that knowledge to the test. With two horses, Kalin and Chet Hawk, in front of us, we all have the relevant data at our fingertips. Let's apply what we've learned from our analysis and consider which horse would you bet on based on this the historical trends we just explored. Length of legs. Kalin has longer legs at 150 centimeters compared to Chet Hawk's at 110 centimeters. Based on our earlier analysis, horses with longer legs have a higher chance of winning. Breed. Kalin belongs to breed A, which has a 55% win rate, while the Chet Hawk is from breed F, which is less successful. T over L ratio, Kaylin has a tummy to length ratio of 0.3, which falls into the favorable range, where Chetak, I'm going to call it Chetak or Jayhawk, is higher at 0.6. Gender, Kaylin is male and Chetak is female. In this case, males have had a lower win rate historically. Head size, Kaylin's head size gives him a 75% success rate compared to Chetak's small head, which is associated with only 10% chance of winning. Country of origin, both horses come from the same country, so no advantages is gained here. So based on our data, Kaylin seems to have the upper hand in almost every category except for gender. If we rely on historical trends we've analyzed, Kaylin might be the better bet. But as always in racing, there is no guarantee and surprises can happen. So which horse would you place your bet on? The attributes of Kaylin and Chetak have changed. Kaylin has a leg length of 110 and a breed of C, TL ratio of 0.5, and originates from Africa with a smaller head size. On the other hand, Chetak has a leg length of 150 centimeters, a breed of A, a TL ratio of 0.6, a head size, a large head size, and is from India. Based on this new information, who would you bet on now? Does this update shift your choices from earlier, or does it reinforce your previous decision? Pausing for a second. So based on the updated data and the historical trends provided earlier, Chetak now appears to be the better choice. With a larger selection of horses, let's apply what we've learned about historical data to identify the best one in this lot. We have various factors to consider, such as length of legs, breed, TL ratio, gender, head size, and country of origin. For example, we know that horses with long legs, specifically around 150 centimeters or more, tend to win 75% of the time. Breeds like A have a winning percentage of 55%, and a favorable TL ratio is generally less than 0.5. Large heads and being from certain countries can also contribute to higher success rate. So as we examine the data, which horse stands out as having the best odds of winning based on the attributes we discussed? Look for the factors that align most likely with historical trends. Now, if we look closely at the table, horse 5 has the highest leg length. Breed A, TL ratio of 0.3, is male and has a larger head size. However, it's from Africa, which is a negative factor. Horse 10 has long legs, 135 centimeters. Breed A, TL ratio of 0.9, is female and has a medium head size, is from Africa, which is again a negative factor. Horse 3 also shows potential with legs of 134 centimeters, breed B, TL ratio 0.5, male, medium head size, and is from Australia, which neither positively nor negatively impact the decision. Based on the analysis, horse 5 would likely be the best candidate due to its strong positive attributes in key areas. Despite the negative factor of being from Africa, it has the optimal leg length, breed, TL ratio, and head size that historically correlates with winning. Okay. In this slide, let's do a scenario. Imagine you are a bank like Citi, facing similar problem. You need to figure out which of your customers might default on that credit card payment or loan, essentially run away with your money. To solve this, you need to predict the probability of a customer becoming a bad debt risk. Luckily, you have historical data for each customer, past loans, payment history, length of credit history, and other crucial details like income, job type, and credit card. Using this data, you can build a predictive model to forecast the likelihood of default. This approach helps you make better decisions about approving or declining credit and helps manage the risk of financial loss. So when it comes to prediction models, one of the most important aspects to understand is the target variable. And we'll talk a lot about target variable in subsequent models. The variable whose outcome we're trying to predict, just like horse racing, where the target variable will be the horse's win or loss. In data analytics, it could be something like determining whether a customer credit application will result in a default or predicting whether a tweet is positive or negative in sentiment. The target variable is at the heart of our predictive models because it is the ultimate outcome we're trying to estimate based on all other data we have. And this is it for this lecture, and see you online in more recorded lectures. Cheers.